I'll get started. My name is Saptak Sen. I'm part of the technical computing team in Microsoft. I'm based out of Redmond, and I've been with Microsoft for actually a couple of weeks back. I completed 10 years at Microsoft, so I'm very proud of it. Today, we are going to discuss developing big data applications on Windows HPC Server. You might have already noticed there's a subtle change in the title. From Dryad, it's now linked to HPC. Now, as we kind of march towards release, our lawyers force us to do certain things. Apparently, somebody in Israel has a trademark on Dryad, so we had to go with a boring name. But I like the name linked to HPC. How many of you have already used Link before? Great. So for you, people who are familiar with Link, it's the simplest way to do analysis of humongous amount of data across a cluster. Means there's no easier path. And for others who are, if you are already a C# developer, VB developer, have a background in SQL, Link is a very easy next step. So with that, let me get started. Okay, before I get started, how many of you were in yesterday's jam session? Any of you? Hats off. You still made it. Yeah. Okay. So, first of all, we are going to discuss about what is big data and why, first of all, what are some of the application requirements for big data applications. We hear about this buzzword a lot, so I think to set a level, let's discuss it a little bit so that we are all on the same line, same page. Then we are going to see how to develop Link to HPC. Not very complex ones. In next about 1 hour, we won't get to complex scenarios, but I'll be throughout the week, I'm in the conference. I'll be at the demo station. I'll also have we'll also have my colleagues at the demo stations. They are probably they know more on this topic than I do. So so you're in good hands. And I'm also going to demo running Link to HPC on DSC. DSC stands for Distributed Storage Catalog. And I'm going to describe this a little bit more as we go along. Any of you actually saw this title, this special report that Economist published last year? They call it data deluge, and by the time Economist creates a special report on something, it's already pretty well known and topic, and people are already looking for a solution. It's when it comes to a mainstream media. So in the last several years, across a lot of industries, the data that all these folks have collected is huge. Also, the rate of collection of data has accelerated, at an unbelievable rate, exponential rate. Just if we look at ourselves, when my dad had a Olympus OM1 SLR camera, and when we went on holidays, he probably used 5 reels, so it's 5 into 32. Snapshots for the whole vacation. We take as many pictures probably in 3 hours time. if we are on vacation. So the rate at which we are collecting data is come to a stage where it's just unbelievable. But what hasn't changed is what hasn't kept pace is the speed at which we can read through that data. Now, if we are collecting all this data all the time over years and years, that's a lot of data. Now, if I have to do a little search, even on my Windows 7 machine, I want to find a picture which I took 8 years back, and do some pattern recognition on it, face detection or whatnot. Sometimes it can, unless I have already created an index, it can take a long time because I'm just limited by how fast the hard drive spins, and that hasn't kept pace. Even with solid-state drives, the data throughputs haven't kept pace with the rate at which we are collecting data or the storage volumes that we have. So now I've just spoken about one type of data which each one of us can associate with. But there are so many, for different industries, there are different types of data that people are collecting, like non-traditional types, like unstructured data, things like call logs. I was talking to a friend of mine who works for one of the biggest carrier in the United States, and he was saying the amount of data they collect just based on people making calls through which cell tower and at what time and so on. They can even predict things like what will be the number of people 3 years down the line on a certain Friday in Times Square, things like that. So that's the kind of data that they are collecting. But all this data is, a lot of this is unstructured, like, say, SMS messages. If you have to make sense of SMS messages for that carrier and do something with it, do sentiment analysis on it, it's hard because there is no database structure you can put all of that. It's just text. There are also weak relational schema. There's also other objects like blobs, like videos, images, and so on. Logs, of course, one commonly known scenario in this case is web logs. Most medium-sized websites have thousands of web servers, and each of them are creating web logs. Any kind of clickstream analysis or anything like that they have to do, or even if they have to detect any unnatural patterns to identify any attacks happening on the websites, they have to go through a humongous amount of data. It's just a couple of weeks back, the whole PlayStation Network, fiasco reminds us that how important it is to keep on top of, these huge amounts of data flowing by. The other paradigm change that has happened is that the distributed parallel processing frameworks have started to emerge and mature. About 15 years back, correct me if I'm wrong, one of the things that happened was the Beowulf clusters. Who remembers Beowulf clusters? Yeah. So that was the first, paradigm change that started to happen from vector processing, from the craze to commodity machines, sometimes tens or hundreds of commodity machines, which you can tie together, use something like MPI, message passing interface, to create a application to take advantage and get you know, similar kind of or comparable performance to those vector processing machines. A similar thing is happening today with data. Means just to go through this huge amount of data, you needed very specialized storage, which cost millions of dollars. And at some point, people are saying, hey, you know, I just can't afford it. Means in this economy, I have to get the job done, but I don't have that kind of budget where I can, you know, sink a couple of $1 million for just one box. Also, as we talked about, large volumes of data has become quite a norm. New economies, large-scale processing and analytics at unprecedented low cost. Of course, also the hardware has overall become more reliable. Means when I think of when I was growing up, when I was going to you know, school or college, the computers I had was much less reliable. Means every 6 months I would have some major problem with the machine. And but in these days, means I have had a machine for last 3 years, and they are very reliable, but they are commodity machines. And the same is happening in the data centers as well, where you don't really have to buy very high-end systems, but you get the same reliability as well as performance from those machines. And at the same time, I can put a bunch of them. Even if some of them fails, they are inexpensive enough that I can almost budget for it. Say, hey, every year I have to, if I have 100 machines, I'll change, say, 5 of them or something like that. Anyway, in 3 years, I have to write it all off and so on. So it's not a big deal. A new data sources has also become, you know, a paradigm changer, like sensors. Like I was saying, means all your mobile phones that you are carrying, or all the devices that you are carrying today, are essentially sensors, and they are hooking up to some place, and there's a way to you know, mine that data. Not to scare you, but there are huge number of devices, web servers, also public data. Means as government becomes open, there are more and more data sets out there, and even non-governmental data which you can do mashups with. So here is a little example of how things used to happen in the first .com boom, where in a traditional e-commerce kind of a scenario, you would have a new user who registers. It goes into a database. He makes a new purchase. You know, he gets a new product. Everything goes to a data warehouse. Now, I have logs. I don't know what to do with it. I run some ETL job, extract a bit of it, but essentially end up throwing most of it, because I just can't store all that data. Even if I can store, I have no way to, you know, search through or, you know, scan through all that data. Like I just talked about the limitation of the hard drives to go. It can't go that fast, basically, the spindles. Today, the scenario has changed a little bit. I can dump all that data into you know, this inexpensive disks, and even have replication. So even if you know, 2% or 5% of the disks fail, I can still recover the data. And I can do things like I can run jobs on it, data-intensive jobs on it to make sense of it pretty much every day. I don't need to index it all. And indexing it only gives me certain types of views. But if I can scan through the data pretty much on demand, I can do much more fun and fresher queries on those. And also, once I kind of munch on that data, I can create an index out of it and put it back, stick it back into the data warehouse. So this is where link to HPC comes into the picture. So just to scare you off to start with, here is a link query, and some of you said you are already familiar with it. So here in this link query, what I'm trying to do is load a log file, then basically search for all the entries which pertains to a certain user, in this case, Sin. And then I want to count up the how many pages and basically write it out. That's all I want to do. So Dryad, which is a very mature technology in Microsoft, Dryad has been in use for over last 5 years at Bing, so it's extremely mature, and the whole Bing search works on it. And on the other hand, we have a Windows HPC server, which has been around for last 5 years, and which is also a very mature HPC management, job scheduling software. And we married the two and layered Link on top of it. Now you can use Link from most .NET languages like C#, VB.NET, or F#. You take your pick. So just to give you a gist of what Link is, Link provides a SQL-like embedded query within a C# or a VB.NET or a F# kind of a language. So it's very intuitive and easy to learn paradigm, especially if you are trying to deal with data from those kind of programming languages. So in this case, once you write a query in Link, our query generator creates a query plan, and that creates a directed acyclic graph, which gets executed on this mature Dryad engine that we have initially created for our search business. So these are some of the stages and how it maps. So all the creation of the directed acyclic graph is totally encapsulated from the programmer. So he doesn't need to think in terms of graphs, what will happen, because in a typical, for a typical query, to satisfy a query, there could be literally tens of thousands of nodes and edges between them. So to do it by hand is extremely cumbersome, counterproductive, and we didn't get the uptake. In fact, our first release of this technology, which is to be called Dryad, as the title of the session indicated, was released by Microsoft Research as a community project, and that had the ability for you to create that graphs by hand, and nobody actually did it. So, so we ended up creating Link on top of it, and or layering Link on top of it, and that was a very natural fit. And that's where we saw uptake of Dryad in commercial enterprises, because that's what developers felt comfortable thinking in terms of, not in terms of graphs and edges, which they can't just fit it all in. It's just too complex. So this is a simple scenario where I input something, I do certain kind of compute, I resort it, and then I essentially, there's a small typo, I output it. So now this is how a typical DAG or directed acyclic graph looks like. The colored balls are the vertices, and then the edges are the inputs from one node which goes, output from one node which becomes the input for the next node. And it's a top-down. We start with the yellow ones, and then the whole thing flows through, and finally when we reach to the purple, we are ready to output the results. It goes through a transformation. Now, how do we map this to physical compute resources? So if you are familiar with any kind of compute or data cluster, there are several types of resources that we have to deal with. Like one of the main types are processors, of course, cores, disks, and memory, and so on. So we basically need a resource manager based on the demands for a certain node, as well as the locality of, at least in the initial phases, where we are dealing with a lot more data. Because as we go through the phases, typically what happens is the amount of data we deal with collapses, because we are reducing in every stage. So the amount of data we deal with, at some point towards the end where we are ready to output, we can start moving those intermediate data across the network. It's not that expensive anymore. But in the initial phases, when I have, say, a 10 terabyte data set, I would like to run those nodes close to where the data actually exists. So, so that's the kind of intelligent mapping that we need to do under the hood without exposing that that confusing thing to the programmers. So that is where Windows HPC Server comes in. So we have a bunch of, say, free compute resources, and then for each of these free compute resources, based on, again, the data locality, the requirements of the certain nodes, they get mapped to certain compute resources. As it frees up, certain nodes get completed. Those nodes free up, then they can take on other nodes and so on. Also, where the intermediate data for the next node is located will determine which node will execute on that particular machine. And as it the whole DAG flows through the resource that we have, everything gets completed, and we can look at the output. So just to map this to more concrete terms, let's say we have a head node here. We have a head node here. And a head node also has the job scheduler, and also it manages the metadata for the data nodes. Now, we have a bunch of compute nodes. Some of those compute nodes can be data nodes as well. You have to determine if you want all the compute nodes to be data nodes or some of them to be data nodes. Let's say in this case, all the nodes we have said, okay, it can also act as data nodes. So that means they will store partitioned data on their local drives. So to start with, let's say we have an application, a link to HPC application, which is essentially a .NET application which uses link and the link to HPC, the libraries. It submits a link to HPC job. It knows which head node is controlling all the resources. So it goes talk to the HPC head node and submits the job. So the head node first, creates a query map. It starts then using based on the DAG, it starts assigning a particular node as the graph manager. So the link to HPC job also starts a set of parametric suite tasks across the distributed vertex hosts. And in the next step, the graph manager actually manages whether a particular vertex runs or vertex runs on a particular node or not, when it starts, when it stops, is it running too long, you kill it there and run it somewhere else. Also, one thing I forgot to mention, when you typically partition your data set across multiple data nodes, you typically have a factor of replication. That means the same portion of data will be on multiple physical machines. So if a certain machine is not responding or not finishing the computation within a particular amount of time, then we can bring up another vertex which requires that particular data set on another node and see if we get the results from it sooner. So even if, say, there's a physical failure on a particular node, your job might not fail. You'll see some failed tasks, but your job might still succeed because there's replication in the data as well as the job scheduler and the graph manager knows that where to rerun those particular vertex to get back the results. So just to kind of dive in deeper around the how the graph manager handles it. So again, the graph manager, which has been identified by the job scheduler, starts and stops the Dryad vertices, and the vertex themselves actually reads the data sets, as well as it writes the intermediate data for the next set of vertex. Another thing I forgot to mention is that it's an acyclic graph. So as this graph is getting solved, it doesn't cycle, in the sense once one vertex completes, you don't go back to the same vertex at some point and loop back. And we don't do that we have certain reasons, because if say, for failover reasons and there are certain other performance reasons that we don't allow that. So let's look at how, if you have a HPC cluster, how do you create a HPC to link cluster? The first step would be to create a cluster. So we have great tools for it. For example, here you are looking at a bunch of templates, node templates. And you can start from this node templates. Then you can tweak this node templates to do to specialize them more. For example, for data nodes, typically you'll go with compute node template to start with. And then for SOA jobs, which we won't discuss it today, you would have one or two broker nodes, and you would use the broker node templates. Then for workstation node template is something which you'll use if you have Windows 7 workstations which you want to use as compute nodes in off-peak hours. And then, of course, the Windows Azure node template if you want to use Windows Azure worker nodes as nodes for as compute nodes, essentially, for your computation. And these are the default nodes. Once you start with these default nodes, you can further add and specialize with more tweakings that you want to do. And actually, I'll show it in action how to do it. Now, the next little command at the bottom of the screen is something which you will run to make a compute node, a plain vanilla compute node, into a to bring it in as part of the DSC or distributed storage catalog, or make it into a data node. So in this case, for example, I'm adding a particular node like sen-cn1. You can typically the names are like sen-cn1, sen-cn2, and so on. And you can even automate that in the naming and nomenclature of your compute nodes on the cluster. /temp path, excuse me, that's where all your intermediate data will remain. /data path, where your the main data sets will stay or persist. And then /service colon sen-hn, that's your head node, essentially. Now, the reason we have separate temp path and separate data path is often people we recommend that they be on separate drives to take advantage of, again, multiple spindles, even on a single computer. Because if it's trying to read a lot of data from, say, the data path, and it's trying to write a lot of intermediate data on the same spindle, it might kind of flood the I/O buses. If you have it on a separate drive, physical drive, then it will be on a separate spindle, and you might get much better performance. So let's look at a little bit of a demo of a tour of what we have. So let's see. Previous. Okay. So essentially, this is my head node, and I'm running the cluster manager software. So actually, it's open here. So let me go with this. So this is how the cluster manager looks like, and this is, as I told you, it's a product which has evolved for last 4 releases, and it's extremely mature. It lets you do a bunch of stuff which you'd typically do, and if you have attended Drew's session on Monday, he would have talked about some of this. For example, one common thing that in any cluster that you'll do is select a network topology. So here we have, say, 5 common network topologies, and you can select from one. There are implications of these, and one needs to know. But the good thing about it is Windows HPC Server manages the whole service model, so to say. Thereby, there is no inconsistency that can happen if you do configuration management manually. So if you are trying to set up the right IPs, the right routing, the right network cards, the adapter orders, and so on, across, say, hundreds of computers, one small mistake on one machine can break your entire cluster. And it's so hard to troubleshoot as to what's happening. So this gives a nice wizard way, and we are famous for wizards, right? So to configure all this to start with. Not only that, We also have diagnostics. So once you've done the configuration and let's say something is not working as expected, there's a bunch of tests, for example, that you can run. For example, deployment environment, MPI performance, network status, troubleshooting, and so on. For SOA applications, if you have all the basics right, and so on. For Excel, UDF offloading, or even VBA kind of application, if you're taking advantage of that, it kind of checks and it gives you kind of a green signals. It detects if something is not right. We also have a LinPack wizard for people who are interested in that, especially with folks who use low latency, high speed interconnects. A LinPack wizard can be used to very easily detect if something's wrong in one of the machines, or even the in one of our customers, the fiber was too tightly bent, and they were having some performance problems. When they ran the LinPack wizard, it was apparent as to which node was causing the performance of the whole cluster to go down. So we provide all these tools. Also, in coming back to the configuration, we have something called, which lets you create images of nodes with the right drivers, with the right configuration, and essentially blast out those images across hundreds or even thousands of machines. We also have, for example, here you can manage your drivers that you need. If it has very specialized drives, you need drivers for those drives, you can include it here. Also, another cool thing that you can do is, if you are really intent on manually installing and configuring a node, you can go ahead and manually configure one node to perfection, and then capture that node, point to that node, and capture that node as your image, and then blast as a multicast to all this over PXE to all the other nodes and configure that. So none of the other HPC solution or even data-intensive solutions out there provides this level of ease of use for the administrators. Now, it also provides a very easy way to do job management. As you can see here, we have a progress bar. There are very deep level of logs as to what's going on with a particular job, the details, how many nodes it's running on, and things like that. Tasks at task level information. If you double click on that, you get to much more, say, allocated nodes, which node, how many cores it's using, and so on. So it provides a lot of granular information. At the same time, it also provides a very top-level information, because administrators often can identify problems just looking at patterns. So here I have 8 nodes. But imagine if you have thousands of nodes, then each of these boxes can represent multiple metrics, and these are customizable. If you right-click and customize the properties, you can put different performance metrics on these boxes, and based on the levels of those metrics, it will have different colors. So when you're running a job, if you can almost see a certain pattern flow. And if that pattern is not typical, you can easily identify that something's wrong. Now, I talked about the management tools, the configuration tools, the job management tools, the diagnostics a little bit. We also have charts and reports. If you want to run a reporting as to things like we have some built-in charts like reports like cluster utilization, node availability, and so on. You can run those reports. Now let's get back to our presentation. We'll come back and run actual jobs when we are ready. So let's look at the link to HPC object model a little bit. Now, for creating link to HPC jobs or even doing anything about it, the first the class that you need to be aware of is HPC link configuration. Typically, the constructor of this class takes the head node as a parameter and gives you back a HPC link configuration object. And then you can set different configurations for your HPC link environment. And then you can basically get a HPC link context out of that. And from that HPC link context, you can either get a DSC service or iQueryable template based on what you want to do. Now, the DSC service, obviously, as the name suggests, lets you interact with the file sets. You can add a file or a bunch of files, and then seal after you're done writing all the files. Basically, through this process, you are ingressing data into your DSC cluster. And then when you want to analyze it, you basically use the iQueryable interface to do that. Now let's look at code to see how it actually looks. So here is the hello world of Dryad or HPC, link to HPC. So the things that you'll notice is that, first of all, the namespace here, Microsoft.hpc.link. That's one of the new parts. As well as here, if you can see that we are using the HPC link configuration constructor to get a config object, and this is my name of my head node. And then I use the same object to get a context. And here I am basically, if I already have a file set, I'm running a link query where essentially it's returning the line length for every line of data that I have, and this could be partitioned across hundreds of nodes essentially, and it gives me an iterator. And then I can find the maximum of it, and by length.max and write it out. So this is the hello world of question. Yeah. Yeah. So we have a SDK which you can download. If you install the SDK, you'll get that namespace and the files. And these are free download. You can go ahead. So let's look at some actual code. So if you go today, if you want, we've just released the beta of Windows HPC Server 2008 R2 SP2, and it's on the Connect site. So connect.microsoft.com. If you go there, you can sign up for the beta, download it, and with it comes not only all you require to run and develop a link to HPC application, but it also comes up with a bunch of samples. And these are those samples, actually. And it also comes with 2 great white papers, which are very informative and great if you want to get started. So the first one that I'm going to look at is the do-pick, because it's simple. So here, what this application essentially is trying to do is it's trying to identify the first thing it's trying to do is copy a bunch of images onto DSC. Once it copies a bunch of images onto DSC, in the next stage, it wants to find out if any of those files are duplicate, although they have the same name, but through checksum, they're trying to find out if it's duplicate or not. Think about Flickr or something, and they have millions of image files, and if they want to, all these cloud services have one problem. You've heard about Amazon starting a cloud music service. You have heard about Google starting a cloud music service. Basically, those are cloud lockers where you put up your music up there, and you can listen to it from anywhere from your devices and so on. That's the promise, at least. So one of the if you had to start such a service, one of the things that you would try to do is to dedupe any files. If say 5 million people have uploaded the same song by Beatles' "Drive My Car," you just need to store 1 copy. You don't need to store it 5 million times, because whoever wants to listen, you just give that same copy back, although they have uploaded it and think that it's their own copy. So it's a very useful kind of example in that way. So coming back to this, just to show you the code. So here, as you saw, we are creating HPC configuration object and creating a context out of it. And things like this, you can essentially you can have change many other configurations. In this case, I'm just changing the name of the job name of this particular example. And here with this, using the DSC service property, I'm trying to find out if that particular file set already exists or not on DSC. If that file set exists, in this case, I'll delete the file set. And you might not want to do that. In your case, you might say, OK, if I find the file set already there, I won't do anything. I can just run the query. So it's up to you. But in this case, in our example here, we will essentially delete the file set. Next, what we are doing is we have a bunch of files in the. So if you look here, we have, say, 4 files. It's a very small number of files. But we are getting all those file paths in a string array called image file paths. And once we get that, we essentially are copying those files onto the DSC, or basically ingressing those into the DSC using a hash partition. Now, now there is a default partition. Default partition in DSC is by files. So every file is a partition. Now, that might not be a good way to go, because let's say if there are different files which are of widely different sizes. So what will happen is there's a big chance that some nodes will have maybe a large number of large files, and thereby it will have no space, and it will have to do a lot more scanning, because you have to scan through all those big files on the same machine. And there might be some nodes which will have a few small files. So the cluster will be unbalanced, as we call it. So to actually get, especially this is a problem, especially if you have many files. If you have one extremely large text file, then DSC will automatically chunk it into several pieces and put each piece on a different node, and that's fine. But if you have many files of wildly varying sizes, there's a chance that your DSC cluster will be unbalanced. So this is where hash partition, and there are many other partitioning methods, and you can implement your own partitioning algorithm and so on. Hash partition basically uses hash to truncate the files in pieces and put it onto the DSC. So in this case, we are using the hash partition. And submit and wait will wait for the submit to complete before this particular method comes back. There's an asynchronous method also, which basically means you don't want to wait. You just fire the submit, it will do its thing, and it will get done whenever it gets done. You can actually check later that whether it's done or not. So in the next part, what I'm trying to do is I'm actually trying to read. So I'm using the from DSC method, and this is my link query, where I am trying to get the checksum. And I have written a small checksum method to calculate my checksum, which basically the get checksum method I have here. So it's a simple hash compute, and which creates the checksum. So through this, I'll find the duplicate files and basically write out which files are duplicate. So let's try to run this program. I apologize. This is a old machine, few nodes. It's kind of slow. Even it's kind of bogged down on the Visual Studio. So let's. So at this point, what's happening is it's loading the 4 images onto the cluster. If it found something, it's deleted, and it's copying the 4 images onto the cluster. Now, one thing to understand is that for any HPC job, there is an overhead for creating the connection, querying, getting the context object, and so on. So if you are having very small work, then the overhead is so large that it's really doesn't make sense. But if you have, say, let's say this took about 20 seconds to get done. Out of 20 seconds, 19 seconds is actually the overhead, and the 1 second is actual work. But if you, so it makes sense if you have, say, millions of images, then that same 20-second overhead is not such a big cost anymore. So it correctly found out that the flowers and the flowers duplicates are the duplicate pictures. And you can download this sample from the Connect site, and you can try it out with your own photo set and go to town. Too many keyboards here. I'm pressing the wrong keyboard. Okay, so let's look at another example. Again, this is a very common example for large big data applications, which is histogram. Essentially, irrespective of where you try to learn a big code for big data kind of application, this is always the first thing that you'd get as an example. So what this particular thing or application does is it tries to count the frequency of words in a bunch of files. We actually tried it out by downloading the Gutenberg repository, and that was a few hundreds of megabytes. That wasn't large enough. It's very hard to get very large text files. Of course, weblogs are very large text files, and we also tried it out on the Wikipedia dataset. Wikipedia actually lets you, if you want to play at home, if you have a cluster, you can download the whole Wikipedia dataset and run a histogram on it. It's kind of fun. But in this case, we have a few artificially created, we didn't know what the licensing restriction was, so we didn't want to ship the Gutenberg or Wikipedia with our samples. So we have some artificially created files here, which are input part text, input part 1 text. They are not very large. So I'll open one of those. It's some gibberish. So what we'll do here is we'll try to, again, first of all, create a configuration object, give it a job name, create a context out of it, and then we will use a load data. Now, load data is essentially my method where I'm using the DSC service object to create the file set, essentially. And then I use the iQueryable interface and create line records from each of those lines of text. And then essentially, I'm creating a split for every word, and I'm using a space or a tab as a delimiter here. And then I'm grouping by word, and then I'm doing a count of those words. So this is my basically key value. This is the key part, and this is my value, which is the count. And then I order by descending, and I take the first 200 because I don't want a scrolling text. So that's all. It's again a very simple application, and so let's try to run this. So let's go look at the job manager in the meantime to see what's going on. So if you look here, okay. So you see it was running and then it finished, so it disappeared. So now it's given the results. You can tell that it's an artificially created text file because it's just So the point of this sample is to show you or demonstrate how easy it is to create big data applications with link to HPC. switch back. So feel free to jump in if you have any questions. I think we've gone far enough. So if I'll try to, in next few slides, I'll try to wrap up and kind of summarize what we have discussed and answer your questions and so on. So please feel free to stop me if you have any questions. So again, as we saw, some of the things we saw are the HPC server administration basics, managing the job queue. You can easily find from the columns. You can actually add custom columns and so on. Which user submitted the job? If a job is running for too long, or it's a non-converging job essentially, or diverging job, you can cancel that job. You can use the dsc.exe. So we saw how to use the API to load files onto DSC. We also have the dsc.exe command, which lets you do the same thing. So you can, and it lets you do a bunch of other things, which the API also lets you do, but this is a command line. If you're an administrator, you would be probably more comfortable with the dsc.exe command line. You can monitor disk usage, view how the DSC file set maps onto physical NTFS across nodes. So for example, you want to service a certain set of nodes. You want to know that if you kind of take it out of service, then which file sets will be impacted, so on. If you want to kind of rebalance the data nodes, you want to find out how many files, how big are those files on each of those different nodes, and so on. Identify the nodes where the files are replicated. So for a particular file, you also want to know, okay, where are the other copies of the same files across the different nodes? Because again, if you are trying to do a service, you don't want to take out all the 3 nodes where that file, a particular file exists, because that will break your, or you'll have a data loss essentially. So just coming back to the whole software stack. So first let's start with the platform. So we have Windows Server, we have Azure. Windows HPC Server takes advantage of both, and Azure, you can see that it's kind of, there's a small color transition. It's because that we are adding more and more features every 6 months on Azure. So we already have a bunch of features in Windows HPC Server for Azure, which lets you what we call cloud burst. So if you have a spike in demand, you can essentially bring a bunch of worker nodes on Azure as your compute node and run compute-intensive jobs there. For data-intensive jobs, in the first release, that will be in summer, you won't have that capability. But by winter of this year, you will again have the capability to run even data-intensive jobs on Azure. That's the platform part of it. The next part of it, the HPC provisioning management, and this is common. This is common across the same look and feel. If you know a particular interface, a particular environment, the PowerShell objects and so on, how to get around, all of that remains the same, and that's, I feel, a big win. And then you have the distributed runtimes. We have the MPI runtime. In fact, last year, we did a benchmark on the MPI runtime on the Tsubame supercomputer in Japan, and the LinPack benchmark results we got was one of the top 4, although it wasn't considered in the official roster. So we didn't get the official position in top 4. but the number we got was right up there. A slight glitch kind of cost us that position. So the SOA runtime is for interactive service-oriented applications on top of the cluster. And linked to HPC, obviously, for data-intensive workloads onto the cluster. So the new box basically shows what are the two different areas which are new. We also now have the distributed storage catalog in the HPC layer, and which depends on the NTFS, which is part of the platform. And in fact, we didn't try to create a new file system simply because NTFS over the years have been tuned and tweaked to an extent where we don't want to start doing that work all over again. We put in a lot of effort. It's one of the best file systems out there in terms of performance, in terms of reliability, stability, and so on. So we just create a catalog which stores the metadata for the file sets on top of NTFS. It's not a different physical file system. So now, from the SQL Server team, we have a product called the Parallel Data Warehouse. And Link to HPC and Parallel Data Warehouse actually complement each other. The Parallel Data Warehouse is for more structured data, and it's a container kind of a thing which you buy along with the hardware, and it's very different from the value proposition that Link to HPC has. So our main target is to the raw unstructured data on commodity hardware to do that well. Of course, Link to HPC integrates well with other tools like Power Pivot, SQL Server, integration services, the Parallel Data Warehouse we've already seen. Of course, it totally inherits all the cool stuff from Visual Studio, like IntelliSense, debugging, and so on. And as you can imagine, this can be one of the pieces of a much more complex workflow, including SSIS or Windows workflow, or you name it, based on your application. So this is kind of the graphical representation of all the different data-oriented properties that we have and how they kind of can fit with each other. So for more information, please visit microsoft.com/HPC, and you can download a eval copy of Windows HPC Server. You can get the Service Pack 2 beta, which will be out in summer, from the connect.microsoft.com. If you go to HPC Server, if you want the HPC Server virtual hands-on lab, basically we have a cluster or a bunch of clusters on virtual machines so that you don't have to install, configure, need physical hardware. If you just have a browser, you can go play with the hands-on labs. If you go to microsoft.com/HPC and click on the technical resources, the links to the virtual labs are at the middle of the page. And at the top of the pages are some great videos which you can watch. Of course, please visit us in our demo stations. We'll be happy to talk with you more about your unique requirements and how we can, how link to HPC or HPC server in general fits or doesn't fit your requirements. There's a certification exam, of course, if you're interested in. I know there's a certification place here where you can go for certification exam. If you're experienced on Windows HPC server, please feel free to go take the certification exam. And you can find me later, of course, at the demo station. I'll be hanging out for quite some time there for today and tomorrow. Also, you can always, send me a message on Twitter or direct message me on Twitter or whatever. Or my email address is saptaks@microsoft.com, so you can email me too. And any questions?